In this problem, you're told that the circumference is 74.7. The measure of arc AB is 123 degrees, which means this central angle is 123 degrees. You want to find the area of the segment of this circle. So the area formula that we're going to be using, the area of a segment is the whole sector, m over 360 times pi r squared, minus the area of this triangle, 1/2 base times height. So the first thing we need to do is find the area of the sector. The arc measure is equivalent to the central angle measure of 123 over 360 times pi r squared. Well, we can calculate r by using the circumference. The circumference in terms of r is 2 pi r. So if we divide by 2 pi here, we get our radius to be 74.7 over 2 pi. From here, we're going to subtract 1/2 the base times the height. So in order to solve this, what we now need to do is work with this equilateral triangle APB. So if we look at that triangle here, APB, we know that this is 123 degrees, and we know that each of these sides is a radius of the circle, so it's going to be this measure. I'm going to go ahead and calculate that here really quickly. 74.7 divided by the whole quantity, 2 pi. Make sure you put that in grouping symbols. And so each of these sides is approximately 11.89. So in order for us to find the base and the corresponding height of this triangle, we're going to have to use the oblique non-right triangle that we have here. It has a pattern of SAS, which tells us we're going to use the law of cosines to find this missing segment AB. So if I call this x right here, I can solve for x using the law of cosines by saying that the side squared is equal to the sum of the squares of the other two sides minus twice the product of those two sides times the cosine of the angle opposite, in this case 123. So if I solve for x right here, I can get my side length, which is the base of my triangle. So I'm going to go ahead and calculate that. I get 11, oops, I'll use the exact answer here. This quantity squared plus the same thing, that quantity squared, minus 2 times that quantity again, all times the cosine of 123. When I get that measure, I now have to again extract the square root here to leave me with x. So if I take the square root of this number and calculate, I get my side to be 20.9 approximately. Okay, so there's my base. So I can plug that now up here in for b, the 20.9 approximately. And so my final step is to come back down here. I need to find what this corresponding height is. Well, when I set up to solve for this corresponding height h right here, I can do a couple different things. I've created this right triangle, so I could use a trig ratio to solve for h. I know that this angle is half of 123, so I could take 61.5 degrees is that angle, and then I can set up my trig ratio that relates these: angle, adjacent side, and hypotenuse. The adjacent and hypotenuse is related by cosine. So I could say that the cosine of 61.5 degrees is equal to adjacent h over hypotenuse 11.89. So my h value can be solved by multiplying both sides by 11.89. And so when I calculate this, again, I'm going to go up and use the exact value, 11.89 times the cosine of 61.5. And when I do that, I get my height to be approximately 5.7. I can substitute that in here, and now I have my whole calculation. So my last step is to take 123 divided by 360 times pi. And I'm going to multiply that by this whole radius, which I got to be 11.89. I'll go up and use that exact value here. Squared minus 1/2 or 0.5 times the 20.9 times this 5.7 value here. And when I hit enter, I get my solution. My total area here is going to be 92.4, and that is my answer. The units are centimeters squared because it's an area. Okay, so all of those steps are necessary. You need to find the area of your sector, which is pretty straightforward, but then you need to break down and find the isosceles triangle that's created inside the figure itself.